Hello, my name is Glen Wurden. Thank you for stopping by my poster. I'm going to show you a presentation on a synthetic model of a laser inverse Compton scattering diagnostic that we have created for measuring runaway electrons in DIII-D. This is in collaboration with Eric Hollmann and Todd Evans. Todd, as you may have heard, passed away at the end of October, so we're very saddened by that. The purpose of this diagnostic is to determine the runaway electron population, its density, energy distribution, and spatial profile in a pointwise manner. This information is really crucial for modeling runaway electron dynamics in disruptions. The existing status is that most measurements of runaways are line integrated, and they're generally indirect. They look at the hard X-rays, they look at the bremsstrahlung, they look at the synchrotron emission generated by these runaways, and then one tries to invert this data and determine the original runaway distribution function that created those X-rays and photons. This is difficult, it's iterative, and generally is under constrained. So we need more measurements. And if we could get a radial runaway electron profile, just like we have a radial profile of density from Thomson scattering from thermal electrons, and if we could get a runaway electron distribution function of energy, just like we have temperature from thermal electrons with Thomson scattering, that would be really great. And in fact, when we do that, it's called laser inverse Compton scattering, which is basically Thomson scattering off of relativistic electron population. So our synthetic model is going to test this out. This has been done in E-beam accelerators, where you've got a nice clean single energy 20 MeV electron beam in this case, with a green laser scattering to produce 14.7 kilovolt soft X-rays, and this was reported in 2002. This measurement has never been done in a tokamak or in a plasma here on Earth. Now, you may know about Compton scattering. That's where the incoming photon scatters off electrons at rest. So here's the incident photon, here's a scattered photon and a recoil electron. And this is called Compton scattering. Now, if the electron is moving relativistically in the lab frame, as the case would be for runaway electrons here, then it's called inverse Compton scattering. And then the photon scatters off of it and in fact gets upshifted in energy. So this is a question of your frame of reference. And then mathematically, we have to transform from the rest frame of the electron back into the laboratory frame. And when we do that, it's nicely done in chapter 5 of Radioastrophysics, a book from 1970. And so we don't have to recreate the math, we just have to program it. Just shows you some more of this beta here. This is the moving electron. V over C is beta. Gamma is the energy of the electron divided by the rest mass of the electron. And so here's the energy scattered of the photon in the lab frame, the final energy compared to the initial energy of the photon also in the lab frame, times this factor involving beta and direction cosines, mu, and gamma. And R refers to the electron rest frame, and L is the lab frame. Well, we also have to do this transformation for the differential scattering cross-section. Here's your scattering cross-section in the initial and final. I refers to initial and final values before and after scattering. The capital I is the intensity of the laser. A time interval, frequency interval, solid angle interval, and the number of scattered photons. So here's the differential cross-section in the rest frame, can be related to the Thomson scattering cross-section, the conventional Thomson scattering constant of 610 to the minus 25. This is why when you do Thomson scattering, you don't get many photons and you need a very bright laser. And for low energies, this all comes back to the standard Thomson scattering cross-section. But we're going to keep the full formalism in our code and then relate the cross-section in the lab frame back to the cross-section in the rest frame by this factor and code it up. So while we're doing that, we can also put in the geometry of the tokamak. Here's the center line of the machine. This is a view from above. Here's the inside minor radius, outside major radius. And the blue is our projected tangential laser beam. The green dot represents the position of our soft X-ray detector. And we can move that all around in the code to try to optimize it. And in fact, the tangential view is in fact the optimum. So the nice thing is that the standard Thomson scattering cross-section, which is unity across here, you can see how big the relativistic differential cross-section becomes if you look at small angles. So in order to take advantage of this forward beaming, we're going to keep a small angle, and this just shows different energies. So from 0.1 MeV to 20 MeV, and the peaking gets stronger and stronger. So we definitely want to be looking at relativistic electrons to take advantage of this. Similarly, the scattered photon is also upshifted in energy by a 4 gamma squared factor, which for the case of an incident YAG laser pulse, 1.17 eV, and a 20 MeV runaway electron, this is gamma of 40, you'd get a photon, scattered photon maximum of 7.4 kilovolts if you look at a small angle. And again, looking at large angles like 45 degrees or 90 degrees, you just don't want to do that. Not only do you lose the differential cross-section advantage, but you lose the upshift in energy too. So the distribution function that we expect in DIII-D, here's a paper from 2015 showing a bump on the tail as what's expected based on existing measurements. And we'd like to take that in our model. Also a small pitch angle at high energies. Basically runaways that are accelerated strongly along the axis will not have a large pitch angle, otherwise they won't be accelerated. So here's our mock-up distribution between 10 to the 8 and 10 to the 9, a few 10 to the 9 bump on the tail, a pitch angle that's sharply reduced at high energies, and correspondingly with a half an MeV of runaways here for the profile we assume, and we can also vary that. Then in this case of 1 joule laser energy input, we would see 10,000 counts, a signal to noise ratio of over 20 to 1, with the background noise primarily coming from argon bremsstrahlung. The argon is presumed here at 10 to the 13 per cubic centimeter, and that's due to the residual argon from the argon ice pellet, which we assume triggers our disruptions in DIII-D. Here we're going to integrate from 100 eV to up to 10 kilovolts for our energy band to create these signal to noise counts. The laser pulse flies through the machine from a large major radius towards the axis and then back out again. And at the same time, the detector solid angle is getting smaller and smaller as the laser pulse propagates along, because you're getting further and further away from the X-ray detector position. Here we assume 20 square centimeters X-ray active area. In fact, we have a 100 square centimeter detector available, and we believe that a 7 joule laser would be possible with a pulse width of 80 picoseconds and a detector gate also of 80 picoseconds. Then we can get a signal to noise of over 100 to 1. Finally, by changing the gate timing of the X-ray detector, we have 4 gate pulses possible on a single laser pulse. We could have 4 spatial measurements across the useful part of the signal, and thereby turning time into space. And so in summary, our MATLAB model suggests it is feasible to do this measurement. We have case studies for various conditions. And again, to summarize, here in yellow is the runaway E-beam, tangential, going toroidally, I should say, and the laser beam assumed to be tangential, incoming head-on into it, and the scattered light coming back towards the entrance window. That's what we'd like to do. And let's see, we don't need the abstract. Let's go here, and just to show you, just this actually is the code here. It's 500 lines in the main code, and there are a number of subroutines that we've written as well. And then here's some example again of the output from the code. So thank you for your time, and I hope you have questions for me.